Right, thanks everyone. Can everyone hear me okay? That's better, yeah. Okay, brilliant. So this is the first time doing this talk. Hopefully you're going to find it quite useful. A little bit about me. I work as a developer advocate for a company called Sonatype. We do dependency management tools. I've personally worked before that as a developer for 10 years in various different languages. Had an interest in cybersecurity for just as long. 3 months into my first job, I got hacked, which was really fun to learn about. I've got a postgrad certificate in advanced security and digital forensics, and this is where I stumbled across quantum computing, in particular quantum cryptography. It was at the start, just before the NIST recommendations came out, and it was just a subject that fascinated me. I don't know about quantum physics, and you shouldn't need to know. Because that's a subject in itself, and if you want to learn about that, you need to go through so many physics things, it is unreal. You need to learn basic physics, then go through that, and then understand quantum properties. We haven't got 6 years, so hopefully this gives a little bit better way of doing it. I've never dated Geordie Shore's Vicky Patterson. That's another Dan Conn. He's an Australian rugby player, as you can see from here. That's where the similarities in name end. He's probably a lot more fitter than me too. Right, so what we're going to start with is, before you can understand the quantum stuff, we need to actually understand complexity. It's a very complex subject. But we're going to take you in an adventure into time and space. Space, class of all problems that can be solved every instant, size n, but in a space growing in a relative constant of the function of n. So what does actually that mean? It means that given a specific amount of memory that grows, this problem will fit in that space. And then we have time. And time is probably a little bit more familiar to us that have been software engineers. It's a class of problems that can solve every instance of size n in a time growing to a relative constant, which is the function of n. And space and time fit very well together. In fact, time is in space. Now, what does that actually mean? Well, when you talk about different complexity classes, you'll find that a lot of them have relationships where they fit inside another. You can think of it like a kind of hierarchical family tree, really. Now, some people think that time and space are completely different concepts. I think that was proven very wrong by Albert Einstein on a physical level. But however, when we're talking about complexity classes, time is always within space. And why is that? Well, someone much cleverer than me, Scott Harrison, he has a book called Quantum Computing Since Democritus. It's an incredibly funny kind of book that has some kind of mythology, but actually understands a lot of these subjects. And what he says is, basically, if you think about a Turing machine, essentially what most computers are built on, they can only ever access one memory point at any one time in each step. So, therefore, time has to fit into space. So then we start thinking around complexity. How do we, there are some things that we actually need to know. And this is classical complexity. This is kind of how our normal bog standard computers work. We think about these things of, well, what is the worst situation I can get myself into? And that's why we have omega as the lower bound. And then some other people thought, well, we don't want to be so pessimistic all the time. Why don't we try and figure out what the rough average is for each time? And that would be theta. And then some people thought, we want to be really optimistic. If there was something that we could maybe get the upper bound on, and that's it. Big O notation. So you might be familiar with these. If you have constant time, it's generally for whenever you read an object from memory. That's something you can fit in constant time. Then we have linear time, which isn't actually on this slide, but that's slightly better than constant time. The one in particular that we will focus on is what happens beyond that. Polynomial time, n to the power of c. You'll find that in fact all problems at the moment that we currently know about probably fit around this time space. And then we have the killer exponential time, which is the inverse of polynomial time, and actually it's incredibly long-winded. I don't think actually there's actually any algorithms that fit in the mathematical sense of exponential time. So once we had this abstract of time to think about, where do we go then? Well, actually, we have, in polynomial time, two very important classes, and I'll probably talk about these quite a lot. P. P is the class of problems solved with a deterministic Turing machine. Now, what is a deterministic Turing machine? It's pretty much all of your computers that you see that aren't quantum. In fact, quantum computers also are deterministic Turing machines. They can only do one action at a time. So you can essentially say on a, I think Alan Turing's paper actually said, if you imagine a very long list of paper, because paper was what computer code was printed on at the time, and fed into a machine, this machine will sit above it, read what's on it, then move to the next. It might shift left, it might shift right. But it can't do anything more than one thing at any given time. NP is non-deterministic. It's essentially the class of problems solved within a polynomial time again, but with a non-deterministic Turing machine. Well, what does that mean? If every single computer that we can see is a Turing machine, what are they? Well, actually, they're just a very abstract concept. Well, why do we need them if they don't exist? Like, that's already a little bit like weird. Well, actually, what this actually does in real life is that it simulates a brute force function. So anything that you brute force or you've needed to brute force, it belongs in the class NP. If you had an imaginary machine that could do more than one thing at each step, so if it could hover over, say, a piece of tape and go, oh, okay, well, instead of reading that, I can read it, store it, and move on 7 in one step. That's what a non-deterministic Turing machine would be able to do. And because we don't have any, it means that actually our problems can't be solved in polynomial time in our classic computers. And then we have a very special case, which is NP complete. NP complete verifies for a single solution with deterministic machines, but will take a polynomial time to search through the whole space in non-deterministic machines. So actually, sorry, I got that wrong. Brute force is NP complete, whereas NP is just a set of problems that can be solved, but they are trickier. So NP complete is very, very hard, and we'll come on to why that is important later. But two more problems that we need to understand are exp time and nexp time. Now, these are the exponential equivalents, deterministic, non-deterministic, and hopefully that's, you're still with us on that. So why did all of that fast 5 minutes make sense? Well, actually, there's a really big question at the moment, because what we'll see is that these classes can, as I said, they're like a family tree. They collapse in on each other. There's a structure that we'll see later on. But at the moment, we'll posit P might actually equal NP, or P might not equal NP. There might be two distinct different classes. Now, does anyone here have any opinions on that? Nope. Cool. That's fine. Many people do. No one knows either, so it doesn't really matter. Why does it actually matter? It's actually one of the biggest solved problems, well, biggest unsolved problems in software at the moment. And the reason is because our whole world is actually built on the assumption that P is not equal to NP. As we see here, there's two diagrams. So you have, on the left side, you have P in its distinct case. You have NP, which actually all P problems belong to NP. And then you have NP complete as a very small subject of another set of problems called NP hard, which is also a set within NP. If P equals NP, well, NP complete is also NP. Now, what does that actually mean in reality? What it means is that brute force can actually happen at the same time as what it takes to to multiply things, or factor different integers. And that actually means, if you think about RSA or other cryptography, that actually blows up. The whole reason that we can have a robust cryptographic system is because we work on the assumption that it's an NP-complete problem to be able to find the factor of 2 integers and that solution, and you can't, it takes a long time to brute force it. If these things take the same amount of time, then in theory, you could create an algorithm that would find the brute force at the same time that that key was needed. So, this is where I sit on the fence. It's a widely held opinion. I don't think P is equal to NP, and here are some reasons why. If we take the premise that P equals NP, no one-way functions exist in that world. You can always reverse it, because you would just do the reverse of that function and get back your problem. Therefore, we have no secure cryptography in the world, which we do. And that would mean that a lot of what we see in the real world around mathematical problems isn't actually right. And I think that that's a bit of a stretch after kind of 60 years in this field. Every proof, so on the plus side of P equals NP, and why it might be a thing, is that every time someone's tried to prove that P is not in the class of NP, then every proof is not robust enough to disclude the fact that P might actually equal NP. That's one thing, right? That's one out of many, many, many reasons for. So let's look at on the flip side that P is not equal to NP. We have working cryptography. No NP-complete problem known so far has been solved in polynomial time, which is what we would need for P to equal NP. And it underpins a lot of our computational class understanding. So what is the problem? Well, Donald Knuth. Does anyone know who Donald Knuth is? He's essentially this guy. Yeah, he looks unassuming, right? Just a friendly old chap. But actually, he's actually probably like the world's most renowned software engineer, or one of them certainly. If people here kind of say about Bill Gates or Steve Jobs reinventing the internet, or being world-class in what they do. Well, for me, Donald Knuth, Grace Hopper, Alan Turing, Gödel, those are the people we should be looking at. What they have done for computing is huge, and they understand this stuff so well. So, what did Donald Knuth say? I mean, it's actually not, I'm not blaming him for the reason that this is, I should make that clear. It's more a kind of joke to say, oh, it's all his fault. But what does he actually say? Well, he says that he thinks that if we had actually a computer large enough, then we might find that P is equal to NP, and that there would be maybe an integer that we would call M that would go through a polynomial. We consider it too large because it's just compute and takes too long, but actually it's a space problem. So if we go back to our original slide where space sits within time, that's why he thinks that maybe P is equal to NP. And mainly, he furthers this by basically saying, even if that's the case, it doesn't really matter, because probably people will never actually be able to implement a polynomial time worst-case algorithm to actually prove this. So he believes it, but actually, it doesn't actually matter. Now, this has all been really good, but I'm guessing a lot of you right here are now thinking, yeah, but dude, where's my quantum, right? I came here to talk about quantum stuff. You've just told me a load about classical computing. Well, the thing is that everything you see now assumes that P is not equal to NP. And hopefully, this will make you think about imagining the world if that's not the case. Because you'd have to think about the world in a completely different way. You'd have to program in a different way. You'd have to assume, a lot of assumptions that we make day in, day out through software change once we decide that P is equal to NP. So this is actually the scale of the problem, though, if we live in a world where P is not equal to NP. This is Greg Kuiperberg. He worked alongside Scott Orison to create what's called the complexity zoo. And I've got references in the slide. So it's a website where you can look at the hundreds, I think there's over like 500 different complexity classes. And they all work on this assumption that we need them. Not just in the classical world, but this is also now moving to the quantum world. If we look a little bit closer on ones that we need for a kind of bit of basic knowledge on it, what we can see is that, what we have is we've ignored space because we know that space is in time, but within time sits exponential time. Within exponential time, you actually have something called p space, which then goes back. So how can time fit in space? Well, space fits in time. And something that's very long can have the capacity to fit something that expands in memory. And what the interesting thing about p space is that you also then have NP sitting within that. And you have NP complete sitting within NP, and you have P sitting in NP, but not equal to it. And that's fine, right? Well, until we think about Monte Carlo algorithms. So Monte Carlo algorithms are essentially algorithms of randomness. You can guess why they're called Monte Carlo. They're used very hugely in gambling. And the only thing that makes what is called is a BPP class. And what that essentially means is, given any input, these Monte Carlo algorithms they are allowed to be wrong no more than 1/3 of times. So 2/3 of the times, a Monte Carlo algorithm will always be correct. 1/3 of the time, or no more than 1/3 of the time, it has to be wrong. So when you're looking at all these different gambling machines on betting odds, they're all still based on, they can only not be wrong 1/3 of the time. So that's why when you see some people getting ushered out of gambling rooms, it's probably because they've sussed that. And they know that, they've watched a machine and they know that even if it's saying 1 in 10, it might have been wrong 10 times. Well, it's got to kind of make that third back. So we can fit these in. Now, this is where things go horribly wrong, because this randomness doesn't actually fit into our nice, packaged, nested outfit. It fits within P space, but it doesn't actually fit within NP, because NP can be solved in polynomial time. These have an error rate. The thing about P, NP, NP complete, well, the thing about NP in particular is that they have to provide a correct answer. There's no kind of movement to be that they're wrong, for example. BPP allows for that due to randomness. You can't always be right because you have yes or no or maybe, right? P, strangely enough, though, can also fit in BPP because P could also, it's just something that happens. And then this is where quantum gets much more interesting. So what can we do with quantum computers? So thank you for bearing with that for 20 minutes. But here's why we need to learn about these things. Because quantum BQP, which is the BPP quantum equivalent, or is it? Nobody knows. But it's thought that BPP fits within BQP. But these whole set of problems that aren't NP, but are P, that aren't NP complete, might actually be able to be solved quicker with a BQP algorithm, and for that we need a quantum machine. So let's try and put this to some real-world things. P, we've said before, is about multiplying figures together, or finding out maybe if a number is prime or not. That's P class. What that will do is, once we have quantum computers, it's thought that we'll definitely get a speed up with those, just because of the amount of space that we get more of, not necessarily the time it takes. Integer factorization is NP, or is it? In a quantum world, assuming that P is not equal to NP, that actually turns into a BQP, discrete BQP algorithm. And what that means is that a quantum computer will make that polynomial time. The same happens with discrete logarithms. And these two things are essentially used for most cryptography that we see in the world today. They are, those things flatten to become solvable problems very quickly. There are, however, some problems which a quantum computer is just not going to help with. And one of those in particular is the traveling salesperson problem. Generally, brute force attacks, of which many are now found. Map coloring problem is another one, where you have, you need to choose like 3 colors and you have a fourth. Where does that go in the subject? That's also NP-complete. And there are 3 sats, which is a Boolean mathematical problem of how to satisfy different clauses over 3 lines. That's also an NP-complete problem. You need to know the area before you actually can fix the problem. You need to take up a lot of space. So none of these problems will actually be solved by a quantum computer. So one thing, if there's anything to take away from this complexity class session, is that when we hear about quantum supremacy, in my opinion, it's a marketing myth. Because you're never going to have quantum computers taking over classical computers. There's always going to be a space for them. And that space is in NP-complete problems where they might actually work a lot better than quantum computers. They might even work faster on them just because of the structure of the complexity of the class behind it. So, now we've got all of that sorted, let's talk about what we're really here for, qubits. Hope you're all having fun. So, back to our binary digits, bits. We know them very well. They're strings of 1s and 0s. They can only ever be at one time a 1 or a 0. So now let's enter qubits, and this is something that is very difficult to get your head around. So what we have is they look a lot different. That's called a bra-ket notation. You can probably guess which part's the bra and which part's the ket. And what that actually means is not really thinking about that as 0, 0. What that's thinking about it is 2 elements that could be 0, 0, or and could be 0, 1, or and could be 1 and 0, or and also could be 1 and 1 at the same time. How does that make sense, right? It's just so confusing. Well, the best way to think about a qubit, and this is why we don't need to go through all of the quantum physics part, is because it's essentially a balance of probabilities. If we think about our old classical computers, they can be 0 or 1, 50% or 50%, right? Well, a qubit also has that, but they have it on what we call a block sphere. Block sphere, so the value of a qubit is actually a determination of an x, y, and z coordinate where that then maps to a particular particular bit. So at the top of the block sphere, we see 0. If a set of coordinates points at 0, that qubit will be 0. And below it, we have 1 at the bottom. And if the qubit is definitively 1, then that will also be 1. But you can see that there is myriad possibilities with this. It's a sphere. And one thing I will actually kind of make clear is a block sphere that's not actually what a qubit looks like. It's an abstract representation of just to try and understand what an actual qubit is. And it's a well-known one. But essentially, if you think about that, if a qubit is a sphere and it's a sphere of possibility, what we can essentially do is that, well, why can't we have a qubit that is half of 0 and 3/4 of 1 or 2/8 of something or a complex number? And the truth is that actually in reality, that's what we see in quantum computers. Each individual qubit could be anything that we want. And why is this? Well, the quantum properties, we have 3 properties that really we only care about today, but there are many more. And if you want, you can definitely look at those. But the ones in particular are superposition, entanglement, and interference. So what do they actually mean? Well, superposition is the best one to understand. It basically just means that it can be in 0, 1 at the same time in one qubit. So if we go back to our block sphere, right in the middle where y is, that's a superposition of that qubit. It's neither 0, it's neither 1. And that fact that you can do that blows my mind every time. And because of superposition, it means that you can basically potentially have many states per qubit. But that's no good just on its own. That's interesting, but it doesn't actually lead you to a quantum computer. So let's talk about entanglement. So entanglement is the ability for qubits in a large quantum state to interact with each other and make a huge probability distribution amongst them. What does that mean? Imagine you have 4 qubits. One says 1, one says 0, one says half. Oh, wow, that quick. Okay, I need to speed up then. One says half 0, and then one says something else. Well, essentially, entanglement means that these are interlocked. They're no longer dependent. And what that will do is that will essentially, what that will no longer do is that they will move each other. So if you change the probability of one of these qubits, you will change the probability of all of them. So interference allows quantum waves to change their superposition. You might have thought that the superposition is locked in one. That's not the case. If you move one, they all move through interference, and the probability distribution moves them to each value of their probability. Therefore, you can make qubits do what you want. You can harness them to then create calculations. And what is an example of that? Well, that's this guy, Peter Shor. Shor's algorithm. It's, I won't go into the details, but it is essentially a algorithm that allows allows factorization of numbers that is thought to be an NP problem, and it scales it down to make it very easy for, in a much faster time. So, where are we with this? Because this is all very straightforward. In particular, the reason I've put this slide in, I'm not affiliated with IBM in any way, but I just love what they've done from a quantum computing side. They have brought out many quantum computers. They actually they're now due to bring out a 433-bit qubit, which is incredible. Now, to give that in perspective, the amount of things that we need to crack Peter Shor's algorithm, we're talking billions. So we're a long way yet, but hopefully within our lifetime, maybe 10 years from now, we might actually start seeing quantum computers with some general purpose laws. There is also another part of quantum computer research, which is working on single purpose ones. If originally it was the EDSAC, then for the very first computer, that was not general purpose. The same thing we're seeing with quantum computing. So, and now we lead to cryptography. So NIST in particular, the main reason in about 10 years why this is a big problem is that, obviously we have NIST that is looking at quantum cryptography, because if Shor's algorithm is true, then that will break all of our current encryption. So we're trying to get ahead of this before that happens. And then we have essentially 5 types that are either better or worse. So you have lattice-based, where essentially all these probabilities are mapped into a matrix of lattices. They rely on finding the correct point in a high-dimensional vector. That is considered at the moment, I think that's recommended from NIST, and that's the most secure post-quantum encryption that we have at the moment. There's also error-correcting codes for encryption. It's easy, but it's kind of, got thrown out in the NIST recommendations. We have multivariate, which also, that didn't work very well. And then we have hash-based cryptography, which is interesting. I'm not too hot on that one, I must say. Or isogenes-based cryptography. And isogenes, again, it's using points on areas to essentially find the mathematical properties of those. For me, I think actually they got thrown out as being kind of insecure. I think there was Bike that was in the final running right until the last end, and then it found, I think, that you can get cracked by rainbow tables. So if you want a bit more information, Scott Aronson not only has a really good book, which I do recommend you get, Quantum Computing Democritus, but he also has a blog where he talks about a lot of these things, Shuttle Optimized. We also at Sonatype have a huge page and learning action on what is quantum cryptography. I've also got some references here, so you can see the various elements of where these things came from. And yeah, thanks so much for listening.
Is this on? Is this on? It's on now. All right, I have a question. Who is still on the bus? Who is still on the bus? Because I fell off the bus on slide 3. Right, I was hanging on for dear life. And really, I don't do a lot of drugs, okay? I don't do hash, I don't do any of that stuff, right? But this talk was fucking awesome. Okay. And I felt like I was doing hash. And the synapses in my brain were like these distant friends trying to catch each other and like, hey, here I am, come and grab me. But no, thank you so much for that great talk. I think I'd love to learn more about this, but I'm going to have to give 7 or 8 years of my life to get to that level. Questions, please, for those of you who are still on the bus, or even those who are not on the bus. I mean, yeah, you're on the bus, right? Okay, well, let me run towards you and give you a microphone. Oh no, this lady will do that. Okay, let's race. Beep, beep.
Thank you. Personally, I'm not sure. I'm not into the bus of P not equals and P or P equals and P. I might say that P is not equals and P because I like my life as it is. So the question that arises now is this. We have some level of safety right now. For example, we have algorithms for hashing SHA-3, 512, or I'm not even sure if there's anything stronger than this. How safe can we feel about this?
Oh, wow. It depends who you talk to. If you talk to some of the people writing these algorithms, no, you should be very scared. But in reality, I think there's an interesting graph on what it actually takes to break RSA, which is at the lowest level of things that we expect a quantum computer to do. And the amount of power and space that's needed to do that and time would mean that we would need billions of qubits. So at the moment, we're at 433. So I think it's a long way off. As I said, I think maybe by the end of my career, I've got another, hopefully, 20 years in me. I think that would be probably the point where we would start to see some actually useful things with quantum computers, but then probably another 5 years would be when you'll start seeing this kind of breakdown.
Excuse me, are you from the future?
No.
All right.
Or am I?
Let's have some more questions. Come on, someone. Everyone's off the bus. Well, it's a very fast bus, right? And congratulations for staying on it. And for those of you who did manage to stay on the bus, thank you so much, and thank you for being in Athens.
No, thank you for having me.
And pushing our P a little further, all right?
Thank you.
Thank you so much. All right, everyone.